All right, so we're going to talk a little bit about water now. All right, so hydrology, study of water, we're talking about the hydrosphere. All right, remember we had the geosphere, which is kind of the rocks. We have the atmosphere, which is the air. We have the biosphere, which is the life. And we have the hydrosphere, which is the water. All right? So a little vocabulary. All right, water circulating between the surface and the atmosphere, water cycle. We have groundwater, we have surface water, and we have oceans. That's what we're going to focus on in this part here. All right, just a little diagram here to show you again what percentage is your salt versus your fresh. You can see the oceans make up, over 97% of all the water on the planet. All right, so let's take a look at this little diagram here. All right, water evaporating from the surface and from soil, places like that, we call evaporation. Water leaving plants and entering the atmosphere is transpiration, and here in neuroscience we combine them together in what's called evapotranspiration. Once we have water in the air, if we cool down the air, we can condense that water vapor, we can create clouds. If we continue to cool it, we can cause rain, precipitation. Once that water hits the ground, a couple different things can happen. One, it can go into the ground and become part of the groundwater, or it can become runoff and go across the surface and head toward the lowest point that it can get to, right, which we call the base level. All right, infiltration versus runoff. These are the two big parts of this. We need to kind of know the difference and when we get each. All right, so ground, slope, and the type of surface itself. So if the ground is unsaturated, means it can still hold moisture, we get infiltration if it rains. If the ground is completely saturated, it can't hold anymore. If it rains again, the water can't get into the ground, so it stays on top and it runs off and heads toward the low elevation lakes, rivers, things like that. All right, gentle slope or flat, you're going to get more infiltration. If it rains on a hill, the water is going to run off before it has a chance to sit and soak in. And then the type of surface. If you've got a permeable surface, meaning one that water can pass through, you're going to get more infiltration. If you have an impermeable surface, one where water can't pass through easily, you're going to get more runoff. All right, here's a little cross section. That little line separating the upper portion from the lower portion there, we call that the water table. That's the depth below the ground where all the pore spaces are filled with water. Right? The area above it we call the zone of aeration, because the spaces between the sediments, between the rock particles, are full of air. And then we call this the zone of saturation, because all the spaces are full of water. And then there's a little zone in between those two called the zone of capillarity, where we get a little upward motion of water into the zone of aeration. And so we have pore spaces that are partially filled with air, partially filled with water. All right, so what are some factors affecting groundwater? One is the porosity. In other words, what percentage of that soil or that rock is empty space? All right? Whatever that percentage is, that has the potential to hold water. All right? If we look at these two pictures here, I got a couple beakers. Right? And in the beaker on the left, we've got some small spherical objects, all the same size. And in the beaker on the right, we've got some larger spherical objects, all the same size. If you look at the look at the one on the right, notice that the larger sediment can't get very close to each other, so we have larger pore spaces. But if you count them up, there's not very many pore spaces in there. Whereas if you look at the beaker on the left, all those little pore spaces are small, but there's a lot of them. So what I'm saying is if you've got two different beakers, one filled with small spherical objects, all the same size in that beaker, and the other one filled with larger spherical objects, all the same size in that beaker, the total amount of water that those beakers can hold is the same. In other words, the volume, the pore space in both of them is the same. In the left, there's small spaces, but there's a ton of them. And on the right, there's large spaces, but there's not as many. But the total percentage of pore space in those two beakers would be the same. They can hold the same amount of water. If you put them under a faucet and filled them up with water and then measured the amount of water that was in it, it would be the same. All right, permeability, we already established what the word permeable means, okay? If a soil or a rock is permeable, water can go through it. If it can't, it's impermeable. And we did briefly mention what capillarity is. That's the upward motion of water through the small pore spaces. So in this particular picture, we've got a porous rock, like a sandstone, that was placed into a shallow container of water. And then they watched over time as the water slowly moved up into the pore spaces of the rock until over an hour later, almost the entire rock is saturated with water. It's almost like a sponge pulling water up. The water kind of works its way up through the particles, and you're going to get real good capillarity if you have teeny tiny little particles, meaning teeny tiny little spaces. That means the water can grab on better and pull itself upward. All right, so the effect of sediment shape and sorting on porosity. All right, so if we look at sorting, what I mean by sorting is all the particles are the same size if they're well sorted. Okay, so in the top picture, we've got shape. On the left, we've got particles that are all different shape. Okay, and what happens is as they get compressed, they kind of twist and turn and they fill in the spaces. So if you look in this over here, there's not much blue. There's not much space for water in here. But notice as we move to this end of the spectrum where all the particles are pretty much the same shape, look how much more blue there is here. There's a lot more pore space in a soil where the shapes are all spherical than if they're all weird different shapes all mixed together. All right? Down here at the bottom, we've got degree of sorting. All right, so on the left, we have poorly sorted soil. Notice we've got teeny tiny little particles all mixed in with big particles. And what happens is those teeny tiny particles will fill in the pore spaces between the bigger particles. And so you can see we have a lot less blue, a lot less water able to fit into this one on the left. Where if you come over here, if they're all well sorted, which means basically all the particles are the same size. Doesn't matter what size, but the fact that they're all the same size. Notice how much blue we've got here. All right, we've got a lot more pore space if we have well sorted particles than if we have poorly sorted or a mix of particles. All right, surface water. Discharge is a measure of how much water goes past a certain point every second. So if you've got a slow moving stream versus a raging river, if you were to stand next to that and measure how much water went past you every second, the raging river is going to have a lot bigger discharge. It's essentially the amount of water, and we measure it in per second, how much water per second goes past a certain point. All right? Depending on certain variables, you're going to get streams having different volumes at different times. Right, so for example, springtime, especially up here in the Northeast, springtime is a prime time for streams to swell because what's happening is you've got snow melt. Anytime you've got snow melt, that water has to go somewhere, and a lot of times when it does melt, the ground might still be frozen, and so it can't get into the ground, so a lot of it becomes runoff, and so your streams become bigger, deeper, faster in the springtime. Also, depending on the climate you live in. If you have a very humid climate, you're going to tend to have faster, larger, bigger streams and rivers. Whereas if you've got a dry and arid climate, Phoenix, Arizona, or whatever, places like that, you're not going to get very many large, fast-moving streams. Right? The particular weather for that day. If you had a nice, dry, sunny day, your streams are going to be fairly small usually. But let's say you get a giant storm that dumps an inch of rain every hour for several hours. Those streams are going to swell up and they're going to fill with water. Right? And then also, depending on the soil type, if you've got a very saturated soil, if it's already full of water and it rains, the water's got to go somewhere, so it's going to flow down and find a river somewhere, find a stream, and it's gonna swell. A couple other terms that we run into when we're talking about this is something called a drainage basin or a watershed. It's an entire area of land that contains a river system. Right? So a river system is one main river, and then there's lots of little tributaries, smaller streams that flow into a larger one. And all the water in that area generally flows toward one location at the lowest point. So I'll give you an example. We have the Mississippi River watershed here. All right? I'll kind of outline this to show you what's going on. But if you see where my outline is right here, see this little area right in here? This is called a divide. A divide does just what it sounds like. It divides river systems. What this means is inside this entire area right in here, this whole area I just outlined, if it rains anywhere in this area, it all eventually flows out the mouth of the Mississippi into the Gulf of Mexico. It all flows into the Mississippi and then out into the Gulf of Mexico. This is called a drainage basin or a watershed. All right. We've got other watersheds. We've got, the St. Lawrence watershed, which has all the Great Lakes, which flows out into the northern Atlantic Ocean. There's other ones down through here which flow into the southern and into the Gulf of Mexico. We got the Rio Grande. We got the Colorado River. We got the Columbia River drainage basins. So there's all kinds of areas around the country. And generally speaking, all it means is when it rains in that area, it's all basically going to go one location. All right? So that's what's called a drainage basin or a watershed. All right, and there it is again real quick. Okay, just to highlight it one more time. All right, just a quick little profile of the Great Lakes, St. Lawrence River system. All right, you can see here, pull this up again here, we've got Lake Superior. Notice it's at the highest elevation of any of them. Also it's also the deepest of the lakes. But the water that's in Lake Superior flows over this lock into St. Mary's River and then into Lake Huron, and it also flows into Lake Michigan. Lake Michigan and Lake Huron are basically the same elevation. I mean, Michigan is deeper than Huron, though. Okay? But the water here flows into these guys. And then these two rivers flow into Lake St. Clair, which actually is considered kind of a minor Great Lake. Right? People don't realize that there's actually another one there, Lake St. Clair. It's really a minor Great Lake. And then into Lake Erie, and you can see the elevation of Lake Erie and the depth. Lake Erie's not very deep. And then the water flows over Niagara Falls into Lake Ontario. And then it flows over a few dams, okay? And then eventually ends up in the St. Lawrence River. You can see really low, and then it ends up at sea level out into the Atlantic Ocean. And that's the general flow. This is kind of like one watershed, all right? So all the water in the Great Lakes eventually ends up flowing through the St. Lawrence River and out into the Atlantic Ocean. So that's a watershed also. All right, so when is the stream fastest? A couple conditions. One, if it flows over a very steep gradient. Okay? If it's flowing down a steep hill, it's going to move faster. Right? It's also faster when there's a lot of water in it. Right? A little trickling brook is not going to move very fast, but a big raging river is going to move pretty fast. And you can see kind of a little profile I've got down here at the bottom. Up here at the top where the river starts in the mountains, we call the headwaters, or the head. And notice how steep it is here. And as it moves through its profile, eventually it levels out until it ends up at either a lake or the ocean. All right. All right, and last but not least, a little bit of oceanography. Okay, not a lot, just a little touch on the oceans. geologists talk about the world ocean. Okay, there's 5 ocean basins, quote unquote, but they're all. I mean, you're not going to stand there and go, oh, look, now I'm in the Atlantic, now I'm in this. Okay, it's all the same water. It's a basin that we talk about. 71% of the surface covered with water. All right, there's our 5 oceans: Atlantic, Pacific, Indian, Arctic, and the Southern Ocean, which is around Antarctica. And we already talked about what sea level is. Sea level is the average height of the ocean surface due to the tides. All right. This is kind of a little cross section of the seafloor, what it looks like. We've got, if you come off the land, you first come into the ocean, it's actually not very deep. I mean, relatively speaking. Okay, it's still deep, but this is called the continental shelf. And then eventually, out a few miles out, it drops off in what's called the continental slope, pretty steep. And then at the bottom of the continental slope, there's a buildup of material that kind of fell down the slope here, and it got compacted. This is called the continental rise. And then the deep ocean basin, what we refer to as the abyssal plain. Right? The reason I'm showing this to you is because it shows both continental crust, and the continental crust does come out under the ocean. See that? All right. So continental crust and oceanic crust, those are the 2 types of crust. Continental crust is granitic, it's made out of granite, 2.7 grams per milliliter is the density. Oceanic crust is basaltic, it's made out of basalt, 3.0, it's denser. All right, salinity, saline, okay, the amount of salt that's in the water. All right. Generally speaking, there's about 35 grams of salt for every liter of water in the ocean. That's pretty salty. Anybody that's ever gone for a swim in the ocean knows what I'm talking about if they've ever gotten ocean water in their mouth when they went for a swim. They know how salty that is. Okay? All right, how does the salt get into the ocean? Well, volcanic eruptions can put minerals into the water, salts, minerals. Okay? Weathering, when water runs downhill, it weathers the rocks it flows over, and some of those minerals get dissolved and picked up by the running water, and then they get dumped into the oceans as the water dumps into the ocean. Evaporation, right? When the water evaporates off the ocean, it leaves some of those minerals behind, so it can actually it can concentrate it. Sea ice, whenever sea ice forms, glaciers in the ocean form, the ice as it freezes, it doesn't pick up the salt. It leaves the salt behind. All right, so how do we reduce salinity of the oceans? Well, freshwater input from rivers mostly. Okay, as the water's flowing downhill, that's fresh water. Okay, it gets dumped in, so that's kind of cutting down the percentage, so to speak. So the processes of adding salt and removing salt and diluting all keep it fairly constant, right around 35 grams per liter. Right? Ice melting also, and then precipitation also. Right? So average ocean depth around 2.5 miles deep. Right? The deepest is what's called Challenger Deep. It's in the Mariana Trench. It's about 7 miles down. That's pretty deep, and that is the deepest that's the deepest we've ever been. We have been to the bottom a couple times. We've been to the bottom of that. I think 3 people have been to the bottom. Okay. All right, here's a little cross section showing temperature. So average ocean temperature is about 15 degrees. This is showing a particular ocean basin where they've got it at 22 at the surface. And then notice as you go down in depth inside the water, look what happens when you get down around 300 or so meters. The temperature just plummets. It just gets super cold, way down to about 1,000 meters. That's called the thermocline. Okay, stays fairly constant for the first few hundred meters, and then it just gets wicked cold right there. Okay. All right, so the ocean temperatures range from about 82 degrees at the equator, 28 Celsius, to about 28 Fahrenheit at the poles. So it's pretty cold at the poles. All right, upwellings. How can I explain upwellings? Deep ocean water is very cold, and it has a lot of nutrients in it. And if the water, and there's also what's called a deep ocean current. There's surface ocean currents, which we already talked about. There's also deep ocean currents. And as this water's flowing around, it brings those nutrients with it, and as it rises to the surface near land, it starts to bring those nutrients to the surface. And you're going to find any people that do like whale watches in Boston and Maine and things like that. They'll take the boats out to these areas where the land rises up, because it brings all the nutrients to the surface, which brings the whales, and it's got their rich fishing grounds and things like that. Okay? We already talked about surface currents. Okay, page 4. Surface currents are caused by the winds. If you were to go to page 4 in the reference tables, looks like this. It shows all the different ocean currents. Okay. What do ocean currents do for us? Well, just like wind, ocean currents move energy, heat energy. They move it all over the surface of the earth. Remember, we said the poles don't get very much heat, and the equator gets a lot of heat, but the earth's not happy that way. So along with the wind, the currents, the ocean currents, also serve to move that heat energy from the equator toward the poles and try to distribute that heat all around the planet. Okay, so here's that page 4 again. All right. Notice something I'll point out one more time. Notice the circulation in the northern hemisphere is generally clockwise. Generally clockwise. Notice in the southern hemisphere, it's generally counterclockwise. Yes, there are exceptions here and there, but it's generally counterclockwise in the southern hemisphere. That leads to west coasts being cooled because the water's coming from the poles toward the equator, and east coasts being warmed because the air is moving away from the equator.